Hi, welcome to the second problem included in our virtual problem solving session about shafts. This is a shaft design problem, and I think it's going to be really helpful for you to complete this week's lab. So we'll jump in. We have a rotating solid steel shaft, which is simply supported by bearings at B and C and is driven by a gear that is not shown, which meshes with the spur gear at D. So if it were shown, it'd be something like this. So gear D, as the problem statement says, has 150 millimeter pitch diameter. The force F from the drive gear acts at a pressure angle of 20 degrees. The shaft transmits a torque to point A of 340 Newton meters, so that is this torque here. Assume the ultimate tensile strength of the shaft is 560 megapascals, the yield strength is 300 megapascals, room temperature and machine finish at the bearing locations. So in this problem, we are going to figure out the minimum required diameter of this 250 millimeter section. So this is unlike our previous problem where you were actually given the diameter. In this case, we have to solve for it. So it's going to require some iterations. It looks like a pretty simple problem from the get-go, but it's, you'll see, it gets a little more complex. All right, so the first thing we have to do is do some shear and bending moment diagrams. In this case, because we only have one gear mesh, so D is meshing with another gear as we talked about, so there's one applied force F. The bearings have to support that total F. Let me draw this a little bit better. So this is the reaction force. I'm going to call it CY, and I'm going to call this BY. And what I'm going to do, because it doesn't really matter what where we place our coordinate axis, so long as we're consistent. So the XY plane I am defining to be this plane here. So it's including, this drawing's getting a little bit messy, I'll erase it, but it includes F, CY, and BY. So those are all in the XY plane. Okay, so we have to do some shear and bending moment diagrams, but to get to that step, we have to do equations of equilibrium. So I will do that down here. We have a simple free body diagram of our shaft, F, BY, and CY. This is our XY plane. Okay, so BY and CY are obviously unknowns, but another unknown, at least up to this point, is F. So how are we going to find this force F? We need to go back and look at our original system. So this force F, this total force, is what is actually inducing the torque at A. But it is specifically the work transmitted component of the total force that is causing the T of A. So that's how we are going to figure out our F, because we're given TA. So remember, TA is 340 Newton meters. So we have TA equals WTR. So WT equals TA divided by R. So we have 340. I'm going to put this in Newton millimeters. Divided by the radius of the gear at D, so 75 millimeters. So we get WT equals 4,533 newtons. And then we have to relate WT to F. So 20 degrees, here's WT, here's F. Cosine 20 degrees equals WT over F. So F equals WT divided by cosine 20 degrees. So our total F is 4,824 newtons. 4,824 newtons. The distance between bearing B and C is 250 millimeters, and the distance between bearing C and that applied force F is 100 millimeters. Okay, so if you feel really strong with your equations of equilibrium and free body diagrams, you can skip this part. Otherwise, just keep following along. I'll go through all the steps. Sum of forces in the y direction equals 0. You have By plus Cy equals 4,824. And then I'm going to do the sum of moments about B equals 0. We get Cy times 250 millimeters minus F times 350 millimeters equals 0. Cy equals F times 350 divided by 250 equals 6,754 newtons. By equals negative 1,930 newtons. So the true direction, should make sense, of By is downward. Now we're ready to draw the shear and bending moment diagrams. So we'll label points A, B, C, and D. There's no shear occurring from the end of the shaft to bearing B. Then we have By, drop down, come across. Cy is acting in the opposite direction of By, so we jump up and over, and then F will bring us back down. So label 4824, negative 1930. Bending moment, remember bending moment is just the area underneath the shear diagram, so we have no area from A to B, so we have no bending moment. Okay, and then to figure out our change in bending moment, we do 1930 times the distance between B and C. I'm going to do this in meters. So 482.5, that's negative, so that tells us we have to go down. The area under the shear diagram from C to D is 4,824 times 0.1 meters. So 482.4. Looks like we had a little bit of a rounding error. I didn't carry all my sig figs when I solved for the bearing reaction at C, but we're pretty close. Close enough. Now let's draw a torque load diagram just for practice. So again, a torque load diagram just shows the value of the internal torque occurring along the shaft. Points A, B, C, and D. And if we go back to our picture, we have this force coming in at gear D, and it's being transferred all the way down the shaft. And you would assume there's some other component here that's kind of taking up that torque or resisting that torque. So we have internal torque all the way along the shaft. This is not always the case. And it's constant and steady. So 340, and this is in Newton meters. Now let's find the values of the mid-range and alternating bending moment and torque. So mm, ma, tm, and ta. And as a reminder, we're not doing this for every location along the shaft, because if you just take a look at our bending moment diagram, the value of the bending moment is changing over the shaft, but we want to look for where the location is critical, because that's where we're going to size our diameter, and that part's really important. So it looks like the most obvious point is where the moment peaks, and that is at bearing C. So we'll take our M's and our T's at that location. So our next step is going to require us to use our analysis tool. So I'll pop over to that now, but this is where we find the minimum allowable diameter of the 250 millimeter section based on both fatigue and yielding analysis. And again, we're basing our specification of the diameter on this critical location, so bearing C. So let's start entering values in. Our SUT is 560 megapascals. The yield strength is 300, so that gives us an unmodified endurance limit of 280. So again, that's half of the ultimate tensile strength. Ka depends on surface finish, and we have machined. So these A and B constants are the updated 11th edition version. So make sure you have these in your tool. Kb depends on the size of the shaft, and that's the first place where we actually have to make an educated guess and then sort of iterate from there. So to make our educated guess for the diameter, which I have as an input down here, let's go back to our figure. So looking back at our initial figure, we kind of have to guess a diameter. So the pitch diameter was given as 150 millimeters. So, you know, something that's obviously less than 150 millimeters. Just eyeballing the figure, I don't know, I'm going to pick 20 as my first guess. And we'll see what we get. So back to the analysis tool.
All right, so I will input my guess for 20 millimeter diameter, and you'll see how that updates KB automatically. We have combined loading, so KC is 1. Room temperature, KD is 1. KE, we have to assume a reliability. I am going to just assume, and I'll update our solution with 99% reliability. So KE of 0.814. KF, we don't have any other information about miscellaneous effects that might worsen fatigue, so just keep that as 1. And then we need to figure out our notch sensitivity. This requires knowledge of both the ultimate tensile strength, which we do have, but also the notch radius. So again, these curves, if you were going to be using these figures, you would have to know the ultimate tensile strength, so we know that, but we don't know the notch radius. So a good guess for Q and QT, a conservative guess at least, is 0.9. That's probably quite a bit high for our situation because we are starting with a pretty low strength steel. So just based on experience, I might lower these to 0.85 or even 0.8, but we'll go with 0.85. So again, the higher the Q and the QT, the more notch sensitive your material is, and usually the stronger your steel, the more brittle it is, so the more notch sensitive it is. So that's kind of the relationship there. For KT and KTS, we don't know the geometry, so we are going to use table 7.1, the first iteration estimates for stress concentration factors. So looking back at the figure here, we're interested in the location C where the bearing is. We don't know if this is a sharp shoulder fillet or a well-rounded shoulder fillet. The figure doesn't show us anything. We know there's some type of shoulder there for the bearing to push up against. So to be, again, conservative, I'm going to assume a sharp shoulder fillet. And let's write down our other assumption, 99% reliability. Now we can use table 7.1. So sharp shoulder fillet, KT is 2.7 and KTS is 2.2. Again, first iteration estimates only. So now we have a first guess for the modified endurance limit, so 157.9 megapascals, and that feeds directly into equation 7.8, where we're going to get a better guess for our diameter. The first thing we need to do is enter in our torques and our moments. So our mid-range moment was 0, our alternating bending moment 482.5 Newton meters, alternating torque is 0, and mid-range torque is 340 Newton meters. Note how I'm going to enter in my moments and torques in Newton millimeters, and that's because a megapascal is a Newton per millimeter squared. So that's going to spit out my diameter in millimeters. So this is just the unit conversion, or the way of thinking about the units that makes sense for me instead of entering things in Newton meters and having to convert later. So 482,500 and 340 with 3 extra zeros, so 340,000. No alternating torque. You'll notice that KF and KFS are automatically brought in from the procedure that we just did. And again, I use orange to show me that I have intermediate values. And then again, modified endurance limit is brought in and the ultimate tensile strength is brought in from this cell over here. So a lot of this stuff in equation 7-8 is kind of recycled from what we've already entered, but again, this is kind of a different routine. So now we're trying to get a better guess for our diameter. So 44.29 millimeters, that's quite a bit different from our initial guess of 20 millimeters. So let's use our new estimate for the diameter, 44.29. I'm going to round that up to 45. And this is a step that often confuses students. So we need to update our diameter, so 45, to get a new estimate for our modified endurance limit. So watch how that's going to change. So our modified endurance limit dropped a little bit. It's kind of like a circular reference. So 144 is now our new endurance limit, and that changes our necessary diameter to 45.44. I am not going to change this right now because I picked pretty conservative estimates for Q, and now would be the time to use our actual geometry of 45 millimeters to update these values for Q and QT to get better estimates for the fatigue stress concentrations. So it might very well be the case that 45 meets requirements, even though equation 7-8 is showing 45.44. So again, this estimate is using more conservative values of the notch sensitivity and hence fatigue stress concentration factors. All right, so let's look at actual geometry. You'll see that I have renovated my tool and put in the Newbert equations to get actual values for Q and QT. This is based on the ultimate tensile strength as well as the notch radius. So let's talk first about how to get this notch radius, which is denoted as R. So for a sharp shoulder fillet, which is what we're assuming, we have an R over D ratio of 0.02. So all I've done here is in this cell for R, 0.02 times 45 millimeters. So our guess for the diameter. So that's going to give us a notch radius of 0.9. So that is one of the inputs we need in the Newbert equations, which again, you need to put in your tool. You also need the ultimate tensile strength. The sort of annoying part is that the Newbert equations are given for English units only. So when I put these in for Q and QT, I had to convert from megapascals to kpsi, and I also had to convert the radius from millimeters to inches. If you have the 10th edition, this routine is actually shown pretty well on an example at the bottom of page 304, spilling over onto page 305. But again, what you can do is try to get these equations in and then calibrate your tool using the figures 620 and 621 to make sure you're on track. Or you can use these values here to calibrate your tool. So like I said before, our estimates for Q and QT when we had 0.85 was pretty conservative. So using this updated geometry, we get lower values for Q and QT, which lowers our values for KF and KFS, the fatigue stress concentration factors. So now those new updated values are fed back in to equation 7-8, so 2.19 and 1.91 for KF and KFS. And that gives us a new estimate for our diameter of 43.88, which is getting really close to 45. So let's do this one more time. It's not going to take a lot of work. Let's just round this up to 44. So I'm going to update this to get very small changes in KF and KFS and SE. So let's see what happens. See those values change just a little bit. And equation 7-8 gets us 43.82. So I'm going to call it at 44 millimeters. Okay, I have one more detail to throw at you here. So why didn't we update our values for KT and KTS? We got these values from the first iteration estimates for stress concentration factors, and we didn't update them because we don't actually have any information about the rest of the geometry of the shaft. So in other words, we know we have a sharp shoulder fillet, but if we drew kind of a zoomed in picture of our sharp shoulder fillet, we said that this D is 44 millimeters, but nowhere are we given this bigger D. And you'll notice that for the charts for KT and KTS, you have to know both the R over D ratio, which we do know of 0.02, but you also have to know this big D over little d ratio. And again, we know the little d is 44 millimeters, but we're not given any information about the big D. So some good estimates for bearings on shaft shoulders are big D over little d ratios of between 1.2 and 1.5. And in your lab, I give you a D over D, big D over little d estimate to use of 1.5. So if we did have that estimate in this case, I like these lines. So we bring it up here. I don't know, 2.8. And our estimate was 2.7 from table 7.1. So since we don't have this big D, again, just to reiterate, we can't really use this table meaningfully. But if you are given a big D over little d estimate, then you can use the table. So all that is to say that I'm just going to keep these KT and KTS values as 2.7 and 2.2 in this case because we don't have that extra diameter information. Okay, so let's finish up the problem. So we're asked to find the minimum allowable diameter of the 250 millimeter section based on both fatigue and yielding analysis. So we did the fatigue part, and now we're going to check the fatigue and yielding actual factors of safety. So I'll try to step you through this line by line. So first we have to find the fluctuating stresses due to bending and torsion, sigma A and tau M. So sigma A is Kf times 32 MA over pi d cubed. And that is here in my analysis tool. That's what this line is here. And then tau M is KFS times 16 TM over pi d cubed, and that is this input here. And so if you have the 10th edition, they're on page 359, equation 7.3 and 7.4. So you'll want to put those in your analysis tool, both for English and metric units. And then the fluctuating von Mises stresses, according to the distortion energy failure theory, which we learned in ME 328. So sigma prime, the prime always designates the von Mises. I won't read it to you, but it is, a combination of sigma A and tau A, and our tau A is 0 in this case. And then sigma prime M is a function of sigma M and tau M, and in this case, sigma M is 0, but our tau M is non-zero. So that's what is happening here, my tool. So you'll see that sigma prime A is not any different than sigma A, but sigma prime M is. So these fluctuating von Mises stresses are found on page 360 for the 10th edition, equation 7.5 and 7.6. Now, a conservative estimate for sigma prime max is just adding the fluctuating von Mises stresses together, And this is acceptable way, I think, to do it in this class. So again, sigma prime max is about equal to the sum of the two fluctuating von Mises stresses. So that's what I have here. And then we can solve for the factors of safety for both fatigue and yielding. So for fatigue, you've seen this before. This is modified Goodman for fatigue factor of safety. So that is what's going on here. So we have a factor of safety of 1.01, which makes sense because we sized this according to a desired factor of safety of 1. And we picked a diameter that was a little bit bigger than the minimum required from equation 7-8. And then for the yielding, it's a little bit easier. It's just the yield strength divided by sigma prime max, so 1.55. So the reason that we want to check the factor of safety for yielding is to make sure that this shaft isn't in danger of failing at first cycle loading. So if you got a yielding factor of safety that's less than 1, then fatigue wouldn't even be an issue because you would expect your part to distort or yield on that first cycle. All right, so yeah, all this goes in your analysis tool, and then that should conclude your shaft design portion of your analysis tool. And as always, thanks for watching, and I'll see you soon.